Man, I wish we didn't have to do order of operations. Hello everybody, and welcome back to Beau Maths. Throughout this course, we have been focusing very heavily on perspectives. That's been one of our big themes. And in particular, the way that theme has kind of presented itself in this unit on order of operations is we've kind of taken a step back and looked at, okay, what would it be like if order of operations were developed differently? And we kind of looked at how that could change math and how that could still be consistent with what we see today. And so we're going to kind of continue that theme today and look at how math could have been developed differently, but specifically by, instead of looking at maybe the order in which we do things like we've looked at in the past, what we're going to do is we're going to actually change how we write expressions in general. And by changing that, we're going to see some very interesting implications for order of operations.
Infix Notation.
So to challenge kind of the way that we write expressions, what we're going to first do is we're going to give a name to how we normally do it. And that's what we call Infix Notation. And notation, that just always refers to kind of how we write something. So this is the infix way in which we write something. So this is the standard way of writing operations. And that's where we put the operation in between two numbers. Right? When we do 3 plus 4, the plus sign goes between the 3 and the 4. And sometimes, because we're kind of focusing on operations, sometimes we call the numbers that an operation acts upon, we sometimes call those the operands. Just kind of a fancy name given the context. Now, one way you can kind of remember the name for this is when we say in between, that's infix, right? So if we consider all of our basic operations, adding 8 and 7, in infix notation, the way this looks is we do 8 and then the plus sign and then 7. We all know this, right? Subtracting 8 from 7 looks like this. Multiplying 8 by 7 looks like that, right? This is all just for reference because we're about to change what we're doing here. Dividing 8 by 7 looks like that. And doing 8 to the power of 7, oftentimes we'll write that as this, right? But if we want to kind of write this in an infix notation where we put an operation in between the two numbers it's affecting, we've seen in previous videos that we sometimes use this little, what's called the caret symbol. Okay, so now what we're going to do is we're going to kind of challenge this notation. We're going to change what it looks like, and we're going to do that by changing where we're actually putting the operation.
Prefix Notation.
So the first way we're going to do this is by using what's called prefix notation. And this has a few different names. Sometimes it's called Polish notation, or PN for short. And sometimes it's also referred to as Łukasiewicz notation. And these names come from the guy who came up with this, whose name was Jan Łukasiewicz. Jan Łukasiewicz was a Polish logician and philosopher, and he's the guy who actually came up with prefix notation. And we're going to discover, as we kind of go through these, as to why he actually decided to come up with these in the first place. And it's quite an interesting idea. Prefix notation, as the name kind of suggests, in pre usually means before, right? So in prefix notation, the operators come before the operands, or the numbers that they affect. So another way we can think of this is as an operator affects the two numbers to the very right of it. Okay, so the way we would write our regular operations then is if I added 8 and 7, that would be written like this, plus 8 and then 7 like that. So what this is saying is that, okay, we're doing addition, and it's affecting the two numbers to the right of it, so that's the 8 and the 7, so it's combining this 8 and this 7. If we're doing subtraction, well, subtracting the 7 from the 8, we do minus and then 8 and 7. So this is going to give us 8 minus 7 essentially, right? Multiplying 8 by 7, same thing, right? We get the multiplication operation before we write the numbers that it affects. Same with division, and same with exponentiation. Okay, so it looks kind of weird, but it's not too bad, right? It's just a slightly different way of writing what we're used to. Now, there is one thing that you might be worried about. If I wrote something like plus 8 to 3, this could be ambiguous. This could either be interpreted as 82 plus 3, or it could be interpreted as 8 plus 23, right? Because addition adds two numbers, but we have three numbers here, so that means two of them have to be a part of the same number. So we either have 82 or we have 23. So how we interpret this is important. So in order to avoid this ambiguity, we always make sure that we just have a space between our numbers that we input. So here, if this was 82 plus 3, this would be plus 82, and then make sure we have a space here and then 3. Or if it was 8 plus 23, we would have plus 8, and then making sure we have a space, then we'll put 23. Right, so that avoids the ambiguity of something like this. And if you were using like a calculator or a computer that was in Polish notation or prefix notation, then what we would do is we would just enter after each of the numbers. So we would do plus, enter, 82, enter, and then 3, enter if we wanted to do the top one. Or if we want to do this bottom one here, we'd do plus, enter, 8, enter, and then 23, enter. Okay, so for our first example, we're going to start by evaluating this expression here. So we have minus times divide 8, 4 plus 2, 3, 5. So how do we go about evaluating this? Well, we already know that the operations affect the two numbers to the direct right of it, right? But if we start with this minus sign, before we even get to the numbers, we've kind of run into some issues, right? We don't have two numbers right to the right of it. We have a multiplication sign and we have a division sign. And similarly with the multiplication, we have an operation to the right of it as well. It's not just two numbers. So what we always do when we're evaluating things is we always start with the rightmost operation when we're using prefix notation. So always start with the rightmost operation, because that guarantees it's going to actually be affecting numbers, right? Okay, so that means what we're going to do is we're going to start with the plus. So starting with the plus, it only affects the two numbers to the right of it, so it's affecting this 2 and this 3. So what we're going to get then is if we write everything else out, then we just replace this plus 2, 3 with what it results in, which is 5, right? Okay, great. Now we move on to the next operation, which is the division. So we're going to be looking at 8 divided by 4, because this division is affecting the 8 and the 4. And 8 divided by 4, we know that is 2. All right, next up we have multiplication. That's the next rightmost operation, and that's affecting the 2 and the 5. So we do 2 times 5, which is going to be 10. So what we're left with is the minus sign, the 10, and the 5. Again, make sure we put adequate spacing so we don't confuse this 10, and we don't combine it with the 5 or anything like that. And lastly, we just do subtracting 10 and 5. So 10 minus 5, that is going to be 5. So our result then of this expression here is 5. All right, so this looks a little hairy, but let's try it out. So again, we start with the rightmost operation, which in this case is the plus, and that affects the two numbers to the right of it, so just the 1/3 and the 2/3. So what we're going to be doing then is we are going to be adding the 1/3 and the 2/3, which is not too bad. 1/3 plus 2/3 is 1. So we write everything the same except for what we just evaluated, which was 1. Okay, so now we focus on the next rightmost operation, which is multiplication. So we're doing 1 times 6. That's just 6, right? All right, next up we have our subtraction. So 6 minus 4, that's 2. And so what we're left with is doing exponentiation with 3 and 2. So that's 3 to the power of 2, which is 3 times 3, which is 9. So that is our result. All right, let's try one more example of evaluating things in prefix notation. And of course, you're going to get a lot more practice in the follow-up exercise video. All right, so this looks a little easier. So we're starting by evaluating the rightmost operation, which is this subtraction. But the problem is we don't have two things to the right of it to subtract. We just have one number to the right of it. Since we don't actually have two numbers to subtract, this is actually not a well-defined statement. Right? So in prefix notation, something that looks like this actually isn't well-defined because the subtraction needs two things to subtract, but it only has one thing to the right of it, so it doesn't work out. That would be kind of like if I wrote something like 2 minus, and then I didn't actually say what I was subtracting off of it, right? This is a nonsensical statement. It's not well defined if we're talking about infix notation because we need another number to subtract off of the 2. Okay, so now let's get some practice converting from infix notation into prefix notation.
Infix to prefix.
So what we're going to do is we're going to take an expression that is written in infix notation, and then we're going to write it in prefix notation instead. And through doing this, we're going to see something interesting, and it's going to actually kind of lean into the actual motivation that Jan Łukasiewicz had when he came up with this notation in the first place. Okay, so we're going to convert this into prefix notation, and to do that, we need to think about the order in which things are happening, right? Because we have order of operations. So we start by multiplying the 8 and the 7, right? So how do you write that in prefix notation? Well, you do multiply and then 8 and then 7, right? The operation comes before the operands or the numbers that you're applying it to. And then we need to take that result and add it to the 1. So what we do is we do plus and then 1 here, because what we can think of this as, since we're evaluating the operations from right to left, we know that this is going to be evaluated first. That's like our first number, because this is going to give us a number, and then we're adding it to the 1. So that's like the second number that this addition is going to be applying to. So this would be the statement in prefix notation. What if I want to do 7 plus 2 times 9 in prefix notation? Well, since we have this in parentheses, we're making sure that the addition comes first here. So we're doing plus 7 and 2. And then we want to multiply the 9 on afterwards. So kind of like what we did up here, we add the 9 and then do multiplication. We know that the plus 7, 2 is happening first. So that accomplishes what we have in parentheses. And then we're taking that result and we're multiplying it with the 9 as dictated by this multiplication, which is applying to the two rightmost numbers, which in this case is this number and this number here. And lastly, what if we tried something like this? So this is pretty much the same as what we had above, except we're just changing the order, which is fine with multiplication, but it's going to look a little bit different when we write it in prefix notation. Of course, the result's going to be the same regardless, but we just have a couple different ways that we can write it. So one way we can interpret this is the same as above, right? Where we say, okay, we do 7 plus 2 first, so we have plus 7, 2, and then we multiply it with the 9. So that would be totally fine. But if we want the 9 to kind of come to the left of them, like we have up here, what we do is we do times 9, and then we do the plus and the 7 and the 2. So what this accomplishes is we still are evaluating the plus first, right? Because that's the rightmost operation. And so this is going to give us a number. So when we do the multiplication, what we're getting is we're getting 9 times the result of this addition here. So it's the exact same thing as this up here. We're just kind of changing the order in which we do these two numbers, right? The result of this is our one number and the 9 is the other number. So we're just changing those around. And that's equivalent to us essentially just changing around the order in which we multiply the two things. But again, it's the same. Okay, so we have a few examples of converting from infix into prefix, but this highlights a very important point. And I want you to try and see if you can notice something that's a little bit interesting about prefix notation as opposed to what we have in infix notation. So assuming you've given that a go, the key difference is that in prefix notation, we don't use parentheses, right? Here we do multiplication first and then we do addition. Here we do addition first, then we do multiplication. But all that corresponds to in prefix notation is just simply changing the order in which we write the operations. Because we always evaluate the operations from right to left in prefix notation, there's actually no need to have parentheses. And in fact, there's actually no need to have order of operations, period. Because the operations are always written in the order in which we evaluate them in prefix notation. There's no ambiguity as to which one we do first. We always just evaluate them from right to left. And this was Jan Łukasiewicz's big idea. This is why he came up with prefix notation in the first place. It's that it basically is a notation in which order of operations isn't necessary. Okay, so prefix notation gives us a notation in which order of operations isn't necessary. So that's kind of cool to think about. Just imagine is if instead of writing things like 3 plus 2, we just wrote it as plus 3, 2, and we did that all along throughout history, then maybe we would never have come up with an idea of order of operations because we would never have needed it. It was just the order would have always been naturally baked into the expressions that we were writing. And so this is a really interesting idea that math could have looked a lot different than what we see now if we had just kind of written these in a different notation. And I think prefix notation is a really nice way of highlighting that.
Postfix notation.
So now what we're going to do is we're going to talk about postfix notation, which, as you might guess, is basically the opposite, where instead of putting the operations in front of what they're applying to, we put them after what they're applying to. So postfix notation is often also called reverse Polish notation because prefix notation was called, well, Polish notation. So here you put the operations after the numbers, or after what are also called the operands, right? So instead of in prefix notation where the operator affects the two numbers to the right of it, now it's going to affect the two numbers to the left of it. Okay, so adding 8 and 7, the way this looks now is going to be 8, 7, and then the plus sign comes afterwards. Subtracting 8 from 7, same thing, 8, 7, and then the subtraction sign comes after. So it's just the opposite or the reverse of what we saw with prefix notation or with Polish notation. So let's say I asked you to do 5, 7, 2, and then minus and times. Okay, so what we do with this is we start with the leftmost operation and we move to the right. So with Polish notation, we started with the rightmost operation and we moved outwards to the left. But here's the other way around. We start with the leftmost operation and we move to the right. Okay, so the leftmost operation is subtraction. So we do subtraction and we apply it to the two numbers to the left of it. So that's this 7 and this 2. So we're doing 7 minus 2. So that's going to give us 5. And what we're left with is just multiplying the 5 and the 5, which is 25. All right, so now let's try this one. It's a bit longer. And keep in mind, this is a 34, not a 3 and a 4. There's no space between them. So, of course, always try these out for yourself first if you're feeling comfortable with it. But we're going to go through this together now. So, again, we always start with the leftmost operation. So that, in this case, is the plus. We start by evaluating 2 plus 6. That is going to be 8. And then we just write everything else out like normal. Now we do the next leftmost operation, which is subtraction. So we're doing 5 minus 9 next. 5 minus 9 is negative 4. And to make sure that we don't think this is a subtraction sign, I am putting the negative a little closer to the 4 with no space in between them. Next up, we're doing multiplication. And this multiplication is applying to the 8 and the negative 4. And a positive times negative is negative, so we get negative 32. Now what we're evaluating is this plus with the negative 32 and the 34. So negative 32 plus 34, that is going to give us 2. Next up, we evaluate the plus, and we get 4. And lastly, we're doing 2 to the power of 4. That's 2 times 2 times 2 times 2, which you will get is 16. So that whole expression evaluates to 16. So it's not too different than what we saw with prefix notation, right? We're just kind of changing the order in which we do it, where we move from left to right instead of from right to left. Now let's do a couple examples of converting from infix into postfix notation.
Infix to postfix.
Okay, so we want to convert 5 minus 7 divided by 2 into postfix notation. So to do this, what we want to do is we want to do the division first, right? We're doing 7 divided by 2, and that's going to happen first. So 7 divided by 2 like this. But what we want ultimately is to do 5 minus this result, right? So we write the division first because we want that to occur first, but then we have to do subtraction next. But what we want to do is we want to do 5 minus this, so we have to write the 5 to the left of everything. So what this is going to do is we're going to say, okay, 7 divided by 2, that happens first. So that kind of ensures that this respects the original order that we had where we do division first. And then we're doing 5 minus that, right? Because the subtraction is taking the two numbers to the left of it and subtracting them. Those two numbers are the 5. And then the result from this 7 divided by 2. So that would be this expression converted into postfix notation. What about this expression here? All right, so we have 5 plus 3 times 2 minus 1 squared. So to convert this, let's just start with the first operation. So the first operation we're doing is this 5 plus 3. So we do 5, 3, and then plus. All right, and then what are we doing next? Well, what we're doing next is we're doing 2 minus 1, right? So we do 2, 1, and then minus like that. And we can write it just afterwards because this 2 minus 1, none of those numbers are really interacting with this 5 plus 3, so we're good to do that. And then what we want to do is we want to take this 2 minus 1 and raise it to the power of 2. So this 2 minus 1 is kind of like our first number that we're raising to the power of 2. So it's going to be our second number, and we're combining those with the exponentiation. So this exponentiation, right, that's taking the two numbers to the left of it, which is the result from this 2 minus 1. So that's what we have here, the 2 minus 1 in parentheses, and then the 2, which is what we're actually raising this to the power of. All right, and then what we're going to do is we're going to multiply the two things, these two statements. And we actually can just do that by writing multiplication, because what that's doing, right, what this multiplication is doing is it's taking the two numbers to the left of it and multiplying them. But what are those two numbers? Well, the two numbers are the result of this 5 plus 3, right? That's this 5 plus 3 in parentheses, and the result of this 2 minus 1 to the power of 2. That's this part right here. So that would be how we write this expression in postfix notation. And again, don't worry, we're going to get a good amount of practice with this in the upcoming exercise video.
Usefulness Comparison.
So postfix notation might feel a little redundant. It's kind of similar to prefix notation, except we're just doing it in the other order. Maybe it's just another way we could have done it. And yes, that is true. However, postfix notation ends up being a little bit more useful and more practically used than prefix notation is. And oftentimes it's used in various coding languages. Traditionally, lots of calculators actually used postfix notation. You might be able to find calculators. Oftentimes they're called RPN calculators, right? Reverse Polish notation calculators. So you may still be able to find some. You can definitely find some online and play around with them if you're interested. The reason that postfix notation ends up being a little more nice than prefix notation is because it works well with something that's called a stack. And we're going to actually go into this in detail in the next video, but I just want you to know that postfix notation actually is kind of a little more practically used than prefix notation is. But again, they're both nice because they both eliminate the need for order of operations.
Concluding thoughts.
But that's going to do it for me today. So I hope you found this video useful, and I hope you're kind of seeing the brilliance of this guy, Jan Łukasiewicz, who just kind of thought, hey, is there actually a way that we could not have order of operations? And he did it in a really clever way, I think, with this prefix notation and then later this postfix notation.
And a couple of videos ago, I also did a video on how we could avoid doing order of operations by using just a ton of parentheses. So it's not really a new idea per se, but when you watch that video, you might have left feeling a little bit unsatisfied from it. And that's fair. I mean, just excessive use of parentheses, it's not all that practical. This feels like a little bit more of a clever way of actually getting rid of order of operations, and it's a lot neater. So hopefully this has been kind of a nice follow-up to that concept. But with all that being said, you have a good one, you stay groovy, and I'm going to see you in that next Beau Maths video.
Beau Maths.